All right. Oh, wow. Are you working today? Section, which one, sorry?
5.2.
5.2. Okay. 120. Does that sound familiar? Ooh, okay. Yeah, that's a good one to ask about. 1 gigabyte is 1 billion bytes of information. $1 billion. How do I write 1 billion? So this is 1,000. This is a million. That's 1 billion. I like 1 billion. All right, so that's that piece. A terabyte is 1,000 gigabytes. So 1 terabyte, yeah, there is 1,000 of these. So really, but for example, what's 1,000 times 10? 10,000. So whatever you multiply by 1,000, you just add 3 zeros onto it. Is that cool? So a terabyte would be this. Anybody know what that number that is? A trillion. Cool. Now we're starting to be able to identify our deficit, for example. You have to get up into trillions of dollars. Hey, I'm sorry. Sorry to bring that up. Who's going to pay it off? You guys. You're welcome. We do a little good. And then Intel developed silicon-based connections that use lasers, blah, blah, move data at a rate of 50 gigabytes per second. So I can move data 50 gigabytes per second. Printed collection of the U.S. Library of Congress contains 10 terabytes of information. So the Library of Congress has 10 terabytes of information. Right? Blah, blah, blah. How long would it take to copy the Library of Congress using these connections? So how long would it take to just copy the entire Library of Congress if they used this speed of data transfer? Now, do you have to know the really, really specifics of this? No. You've all used flash drive before, thumb drive? Yes. Or some kind of thing, or moved data from your phone to your computer or something. So that's really what this is talking about, right? Just huge amounts of data getting moved around. So if the Library of Congress is 10 terabytes, what is this? So this is a trillion, so this would be 10 trillion, right? So this is where scientific notation comes in really handy. What would this be? 10 trillion. 10 trillion. It would be 3, 6, 9, 12, and then one more. So it would be 1 times 10 to the 13 bytes of information. I didn't have to, no. And then 50 gigabytes per second would be what in scientific notation? Do you guys see what I'm doing here? I'm turning things into scientific notation, so I have smaller numbers to look at. So there's 2 things going on here. One thing is, if I could move 10 bytes per second, and I had to move 500 bytes. All right, can anybody tell me how long it would take me? What do you do to figure out how long it's going to take you? Divide. Right, divide what by what?
500 bytes by...
Yeah, so divide 500 bytes. Divide the amount you got to move. Divide the amount you've got to move by the speed. By the speed. And that would be, of course, 50. So it'd take 15 seconds. Now this is going to take a little bit longer. But, okay, so why did I do that? Just to give us smaller numbers so we can see what the hell to do with the big ass numbers, right? So very often if you can make a similar problem with easier numbers, instead of 50 gigabytes and terabytes, maybe use 8 and 4. See what your brain does, because your brain can latch on to that shit. Your brain can't really latch on to this shit too. So don't feel bad if you can't, it's fine. So now I know I want to divide. And then the second layer of this is related to problems earlier in this section. Can you divide, what you got, Jeff? 6 times 10 to the negative 8 divided by 2 times 10 to the negative 5th. Can you do that? And I argue you should be able to, right? I'll do some of this. 6 divided by 2 is 3. Okay, I contributed. Every time you do that, Jeff, it just gets funny. What do you do with this?
You have to switch to negatives, right?
Yeah, you could.
Bring the negative down.
Yeah, you could. But we could be smart about it. Don't I know I want this to be times 10 to the something?
Yeah.
Right? So don't I want all my 10s up top no matter what? So then if I bring this up, what does it become? 10 to the... It's negative now. If I bring it up, what's it become? Yeah. The negative 5 tens want to go up and become 5 tens. If you move them, the exponent has got to change sign. And then how many tens do I have? Negative 3. Okay. So, I don't know if you guys see the connections yet. I'm going to have to divide things written in scientific notation. That's how you divide things with scientific notation. Right? Another example, if I had, what you got, Jeff? 9 times 10 to the negative second divided by 3 times 10 to the ninth. So I'm not, what's driving me here is the form I know the answer is supposed to be in. It's supposed to be number times 10 to that. I want everything up top, everything up. I don't give a shit if it's got a negative or positive, I just got to move it up. So what's in the wrong place?
The 9.
The 9 tens are in the wrong place. If I do move them up, what's going to have to happen?
It's going to go negative.
Yeah, it's going to become negative 9. 9 divided by 3 is 3 times 10 to the negative 11. I like it. So I'm not changing the rules. I'm not saying negative powers don't flip. I'm just saying my focus is bring all the 10s up because that's what the answer is supposed to look like. So if you do move something, if it's negative, it becomes positive. If it's positive, it becomes negative. That's what the power means. Okay, one way I look at negatives, with the sign on the exponent tells you where the thing wants to be. That's negative. It doesn't want to be here, so if it's up here, it's happy. That's happy where it is. If I force it up now, it doesn't like it. That's another weird way to look at it, but... No, yes, that was a definite weird... I didn't do it. You still got to do it. But I gave you the skills behind how to do that problem. That is one of the harder problems, yes. Yeah.
So is that 5 times 10 to the 10?
Yeah, because up here, one of these would be 3, 6, 9, and then 10. So 5 times 10 to the 10th. I like it. So that's how to convert that. And then you make the division, and it becomes a problem like this. Maybe, maybe. You should be used to the idea of a problem having multiple steps to it. And you shouldn't automatically give up because that's true, right? Or it's up to you. You can't. You get nowhere. That's up to you. Anything else from homework stuff? Chris, did you have something? Did you have something?
Yeah, so it's the same 152, number 27.
Oh, okay. So 27, maybe it's confusing because there's not a lot to do.
There's not a lot of,
There's
the
not a lot to
variables
do.
are the same, so.
There's not a lot to do.
Yeah.
What's the only thing you can do?
Flip the
Yes.
exponents.
Flip the things with a negative power. Kick ass. And that's it. So
Okay.
that is confusing because it's like only one thing to do.
Oh, so
I like-
I'm literally just changing the top and bottom?
Yeah.
Oh.
Well, no. Only those with a negative power, right?
Yeah, there's 2.
Yep. just move those and you're done.
Okay.
Yep. Who had?
Yeah, it was on 5.3, number 75, and then on 85.
75?
Yeah, and 85.
Oh, yeah, all right.
Word problems and stuff.
So, I forgot to look for my little shirt, and I could totally geek out, because I don't know if you know what day it is today for math people. To be really honest, you know, I have fun with it. We got pie in the office, you know, we go a little crazy. We drink and we get drunk, eat pie, and smash pie all over and throw it around. Why is it pie day? Yeah, because pi is approximately 3.14. It's an infinite number of digits after that, but that would be March 14th. And the next two digits after that are 1-5. So in 2015, we had Super Pi Day, and you better have stayed out of our freaking way. We were going insane. I was at a conference. It was Super Pi Day. It was yeah, just as much of a throwdown as you can imagine math teachers are capable of.
What's your favorite pie?
My favorite pie? I go for apple pie. I'm a traditionalist in that, with some Cool Whip on that damn.
Oh yeah.
Fresh out of the oven, Cool Whip, apple pie. Yes. I won't turn down anything. I like it. Big pumpkin pie. Yes.
Vanilla with warm caramel on top.
Ooh, interesting. Warm caramel.
They have like the crumb apple cakes. Or like
Yeah.
caramel.
Dude. Don't get me wrong. I won't turn down. There's not many pies I'll turn down. Anyway, so what the hell was I going to talk about? There was something.
Pie.
Oh, pi. Okay. So this one tells you use pi 3.14. They say approximate pi. Please do that. Never tell somebody it equals this. It's approximately 3.14. And they give you the formula, I think, right? Hopefully this is one you might know. Circumference of a circle is 2 pi r. In fact, real quick, because it's pi day, and because this question deals with pi, where the hell does this pi come from?
The symbol. Or like the number.
It's really freaky. This is why did we give this a symbol? No matter how big of a circle you got, right? Think of a circle as large as the Earth. If I take the diameter, right? If I take the diameter and divide it into the circumference, no matter what, it comes out to be the same number. And different civilizations had different estimations for what this was. One estimation was 22 divided by 7. If you do 22 divided by 7 in your calculator, I can't remember exactly what you gave me, 3 point something. It was their approximation for it, which is pretty damn good before supercomputers came along, and we can get to the 5 millionth place of pi now. It's crazy. But this ratio, no matter how big or small the circle was, came out to be the same number. And imagine people that didn't know that, and you're all like, why would they look at that? But they did. And it freaked them the shit out. Of course it does. Right? They're like, it's a bigger circle. This ratio is the same. Now, on one level, hopefully, it kind of makes sense. If it grows, everything grows by the same amount. But why would it be 3.14159, blah, 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 blah? Right? That's gotta say, it's a little nifty. It's like a fundamental number related to nature. So yeah, we gave it a letter. Shit. Right? And that's where this formula came from. Does that look familiar at all? And of course, what's the diameter related to the radius? The diameter is... Huh? Yeah, so how big is the radius compared to the diameter? Halfway. So diameter is twice the radius, right? So that's where 2 pi r comes from. Replace d with 2r, and you get 2 pi. So cut to the chase. Everybody cool? You alright?
No,
What happened?
I didn't have pie today. Yeah. Well,
It's too bad. Come to my office. Maybe get a piece of pie. A piece of pie. This one tells you find the circumference with 75, right? If the radius is 10 centimeters, and now it's just plug and chug. You put that there, you put that there. Throw on the old calculator. Is that cool? Yeah. I like it.
And then I had a question on 85.
85. This was 75. Section 5.3. Oh, 85, I love this one. You would never think that this function means what it does.
I just got confused because it said that I had to refer to 79, so I thought I had to figure out 79 to get 85. Oh, wait.
85.
Oh, wait, never mind. I see.
80 says see exercise 79.
Yeah, but then I got that whole thing. 75.
85 is tricky, okay. This one is the number of balls in a pyramid that you create. So like the bottom layer would have 9, possibly. Second layer would have 4. So you can see pictures in the book about how to make a little pyramid of like tennis balls or something. The number of balls given the number of layers you want. So this would be the number of layers, x. So you can imagine like the base has 9 tennis balls. 9 tennis balls. And then on top of that you can put 4 tennis balls. And then 1 at the top. Right? So if I put 3 in here, it better come out with 9 plus 4 plus 1, 14. So then they ask you, I think that's what they asked. Yeah. And then they ask you for, how about 5 layers? So it's really just plugging a 3 in, and then you plug a 5 in. What you get freaked out about is, I mean, there's no way in hell you look at this and realize that that represents something like stacking tennis balls, right? And that is one key thing about mathematics. You put a lot of work, there was a lot of work went into developing this. But this doesn't look like it has a connection to where it came from. That happens all the time. And either students lose faith in what they're doing, or it's just disconnected so they forget how it connects. I understand that. But this problem really is just plug and chug. Put a 3 in, plug a 5 in. Cool. But see, for 3, we know what the answer should be. 9 on the bottom, plus 4 is 13, plus 1 on the top. So it should come out to be 14. When you plug a 3 in. Yeah. Okay. Anything else from homework stuff? Yes?
5.4, number 70.
Oh yeah, good. I love it. Let's see. Oh, yeah. All right. So the weirdest part of this question is it says your deck is y yards, right? Yards, can't remember. By y yards. So you have the square feet.
Yeah.
Okay. Y feet by y feet. So can you draw that? So your back deck is in the form of a square. Draw it. And it's y feet by y feet. So what would that look like? It will look like a square, Jeff.
Yeah, y by y.
Y by y. Now, it says in the middle of this, or somewhere on this, you put a 5-foot by 7-foot jacuzzi. Now, you're hoping that your deck is bigger than that, or else you guys are dark. Might fall over if you get to the edge. So you want it to be, and is it circular? 5 foot by 7 foot, so it's, thank God it's a rectangular jacuzzi. So here's 5 foot by 7 feet. And what they want to know is what's the area of the walkway around jacuzzi. I call this problem a cookie cutter problem. What's the area before I put the jacuzzi down?
Y by y.
So the area of the outside, careful, what's the area?
Y squared.
Y squared, thank you. Right? Length times width. How big of a cookie am I cutting out of it? Because I used to be able to walk all over my deck.
35 squared.
Huh?
35 squared.
Yeah, minus the area of the cookie I cut out of the middle. So I'm trying to figure out what's left. So can you imagine some dough? Somebody rolled out, somehow it's in the form of a square. And then I cut out of the middle 5 by 7. So what's left is really the question. What's the area of what's left? I pretty much just did it for you, damn it. That's the answer, obviously, right? What number? I didn't mean to, but oh well. And what's the units going to be on this? Yes? There's a gimme. You're all like, yeah, Jeff, that's fine. I get so interested in the problem, I got to work it all the way out, and you're all like, sounds good to me. All right. Anything else? Homework? I like how you guys asked it in the order of the section. That's kind of nice. That, and 5.4 is actually, we haven't even officially gotten there yet, sort of. Let's see, do I want to do much in here? Maybe. Just put this up here. Yeah. So if you got your green book, look on page 87. Maybe I won't even put it there. I'll put it over. I don't feel like doing the overhead today. Section 5.4 is the part that we've done before. It just wants to put them in the context of polynomials. So we're going to add and subtract polynomials, which is really just a review of like terms. So look at, if you got your book, look at number 4. Oh, I'm sorry, number 3. Let's do number 3. So let's see, this says 5x squared plus x cubed minus x minus negative 5x squared minus 4x cubed plus 3x. So we talked a little bit about this last time. What's the thing in this problem that's going to trip the most people up that you've got to be most careful about?
Negative.
Yeah, the negative. What am I subtracting in this problem? Subtracting all of this.
So distribute.
Distribute. I love it. So you got to distribute that negative. So it's a good idea to rewrite this. So minus and negative. Minus and negative. Minus positive. Yeah, what's in front of this parenthesis? 1. So it doesn't, I can just get rid of it. Bring a 1 through. Nobody really cares. Poor little 1. You guys with me? Now at this stage of the game, if you still don't understand like terms, you are behind a lot. You need to know like terms. So this section should be relatively easy. You just got to be careful about the problems where you're subtracting a bunch of things. And so what goes together with this dude?
5x squared.
Yeah, let's put it in order at the same time. What should I put first? Use x cubes, right? So how many x cubes? 5x cubed, and then the squares come next. And of course the poor little x's. Yeah, cool. They're coming too. There we go. Shabbat. So that's in what's called descending order. I like it.
You want us to write it in descending order?
Yeah, start getting used to that. Yeah. Before now, it was just about identifying and all that kind of stuff. Now, we should start getting used to putting it in descending order. It's just convention. So what about number 4? Try that one.
Oh yeah. Look at that. Yeah, man.
real math problem. Please stand. It's not quite that. Now, this one's not as bad as this one in one way. There's a plus here. So you can just ignore the parentheses, right? Because there's really a 1, so nothing's going to change. So you just start throwing like terms together. But this is where I start to get people not really understanding like terms as much as they should. What can you put with the m squared term?
M squared.
The other m squared term, right? And what can you put with the mn? The other mn. And what can you put with the n squared? The other n squared. But somehow people start putting more and more things together. I have somebody that'll do this. You ready? 5, 6, 4m cubed n cubed. That's the kind of thing I would see. Can you see how this person got that? You got 5 of these, plus 1 more is 6, minus 2 is 4, and 3 m's and 3 n's. So what I would say on this person's paper is, I don't see any m cubed n cubes. How the hell did you get 4 of them? Do you see any m cubed n cubes in here? I really want you to look at this the right way. I'm claiming there's 4 of these. I don't see any of them. So how in the world do you get 4 of them? You guys with me? That is the correct way to look at this. So I see 5m squares minus 5m squares, so all my m squares die. And then I see an mn minus 3 mn's. And then I see negative 2n squared plus 7n squared. Plus 5n squared. Yeah. I like it. Now this one, in terms of descending order, it's a little bit, do you see why it's a weird? I have m's and n's. I wouldn't really ask you to put this in any specific, do you see how it's descending order in terms of m? And it's ascending order in terms of n. And we normally do that alphabetical thing, right? If I had p's and q's, I put the bigger p's first and the bigger q's last. You guys get that? That idea of alphabetical order tells me who's going to go descending, who's going to go ascending. Maybe. Yes?
Why isn't there the 5 no wait,
They cancel out.
okay, they do?
Yeah, you got 5 of them here, and you lost 5 of them there.
So does it exist anymore?
0. Yeah, they don't exist anymore. Bob minus Bob is no Bob. It's gone. Bob is dead, or somewhere else. I don't know. Kill Bob in this problem. All right. Blah, blah, blah. Oh, okay. That's enough of that. So section 5.4, there might be a little weirdness towards the end of that section, but for the most part, it's just like terms. So you got to come at me with specific questions. I want to devote most of the day on multiplication and maybe some division of polynomials. You're going to love it. I just don't feel like using the overhead today, so I'm just not going to do it. So this is section 5.5. So if I do, all right, if I do a monomial times a monomial, that sounds horrific, right? Monomial times a monomial. These are the problems we already saw back in section 5.1. This is something like this. So guys, what's really nice about polynomials is what cannot happen in a polynomial. What kind of power will I not see?
1, 0, 1.
Negative?
Negative, for example, right? And these kind of problems, we've seen them before, haven't we? 5.1, 5.2 has a bunch of problems with this, and when they have negative powers, it gets all freaky. So it's beautiful. I'm not applying polynomials together or dividing them. There will be no negative powers. There cannot be. So this is old news. What happens here?
3 times, oh, you want us to do it?
Yeah.
4 times 3 is 12.
Yeah, 12.
X 3.
X 3, got 2 there, 1 more.
Yeah. And then
3 there, 4 more.
That's the other.
Cool, is that all right? So we're finally going to see today problems where I have to distribute, where I have to FOIL.
Oh,
And I think I told you already that personally I wish we never taught FOIL. And if you love FOIL, hopefully by the end of the day you'll see why I feel the way I do.
FOIL sucks.
Anytime we tell you guys a mnemonic device, FOIL, to me it makes it seem like, oh, if I didn't know that, I could almost not do it. It's just too hard. When really it's just repeated distribution. So we'll see what the hell that's all about. So what if I do a monomial times a binomial? So what would that look like? That might look like this. Negative 6ab squared times, what you got? 2ab cubed minus 4ab. Yeah. So this is just distributive property, right? Like it. And what would order operations say about this? I really am supposed to do what? Inside first. So distributive property is not breaking order operations. Just to remind you guys, I'm pretty sure I showed you this before. If I have 2x plus 1s, I can't do x plus 1, so I can't do order operations. But order operations cannot be broken. Right, it's a rule. But I can rewrite this as 1x plus 1 plus another x plus 1. So I'm reorganizing the work I have to do. I can't use PIMDOS directly. Let me rewrite the question another way. And then I've just got like terms. 2 x's, 2 1s. So screw this step. I go, oh, there's a shortcut. I'm going to have 2 x's and 2 1s. You guys with me? Okay. So here, I just kind of use that same concept. This, what do I get here? Yeah, see how these are, it's just like 2 of these problems in one problem. So negative 12a squared b 5 plus 24 a squared b cubed. Kick-ass. Okay. So let distributive property be nice. I like it. So of course, what am I going to do next? Binomial times binomial. Yes?
Quick question.
Yes.
So when you're doing b squared and the b cubed, you wouldn't multiply that, you would add them?
I am multiplying b squared times b cubed.
Okay.
Totally am. But if you say 2 times 3, that's where come at you again with there is no 2, there is no 3. There's 2 b's times another 3 b's.
I got you now.
Yeah, good. Is a list of 5 b's. You guys with me? It's really easy for your brain to go, dude, I got this. I know what 2 times 3 is. And a 6 goes down, but you gotta like stop. Yes?
It helps me to think about it how you told us in terms of going down a step, because it's separated by multiplication, so you know you're going to add the exponent.
Yeah, it's like whatever, however many A's and B's, they're both going to get 1 more A and 2 more B's. That's kind of like, so there is 1 of each. 1 more A is 2 and 2 more B's is 3. I like it, I like it, I like it, I like it. Alright, so here's the next level. Let's do a nice, easy one to start with, just so I can...
Bye.
Yeah, thankfully it's not 3. Right? Bye. That's what back ways. Let's do a nice small one so I can really see what the shit's going on. I know you know how to do this. And I know you know FOIL. Who actually uses FOIL? Anybody? You use FOIL? You know, huh?
In other classes.
Yeah, but so you've used it before. So here's why FOIL is not necessary. really want this to make sense. Now, okay, just let me do this. I want to show you why it works the way it does, and then show you a better way to look at it than FOIL, and then really show you why the shit FOIL sucks. Yes?
So in the end, would you want us to use FOIL?
No. I want you to understand. FOIL is a mnemonic device to remember a process that's easy already. The only problem I have with it is it makes it seem like it's got to be hard, and that's why they came up with this FOIL thing. Does that make sense? Anybody know what every good boy does fine means? My musicians, it's kind of remember the chords, right? That kind of makes sense to remember the order of the chords. This, I don't need that. So watch. Stay with me. Never do a problem like this. You know I do this. I'm going to show you why something works the way it does. This is just the same as this. What am I distributing to x and 3? X plus 1. Again, do not do the problem like this. Maybe don't even write this down. But I'm going to show you why it works the way it does. So I'm going to do the exact same thing because math can't change. Whatever's in front of things gets distributed. So what's x times x plus 1? Let's break that down. Plus 3 times x plus 1. Right? No? So what did I do? So let me put this here. Watch. Let me put it on this side. What would you do here?
This should be.
So it'd be this times x and this times 3, right? If I put a 7 there, it would be 7 times x and 7 times 3. If I put an x plus 1 there, it'll be x plus 1 times x plus 1 times 3.
Same thing.
The idea can never change. Just there's got to be a shorter way to do it. So we make a shortcut to this, right? Because what really ends up happening next, well, now I just got this, right? X squared plus x. So what really happened, the x distributed, and then the 3 distributed, plus 3x plus 3. So that's what I mean by repeated distribution. Now stay with me. I don't mean to make this sound harder, which when I show you why things work, that somehow feels like I'm making it harder. It's obviously not my job. I could do that really, really good, but that's not my job. Let's do another problem, but do it without the extra step in it. And then I'll show you where FOIL goes to shit. So let's see. 4. So say I have 5x minus 2 times 4x plus 3. So I know most of you guys can just eat this up for lunch. Hopefully some of you guys. But again, 5x gets a turn, and then negative 2 gets a turn. That's the right way to look at this. What is the fundamental idea? I'm distributing something to these. Right? How many things? 2. So they each get a turn. So 5x gets a turn. 5x times 4x is
20x squared.
20x squared. Good. The square is the most forgotten thing, which makes the rest of it crap. Right? So you got to remember that. And then 5x goes to 3. 15x. And then the negative 2 gets a turn. I don't have to use FOIL at all. What am I doing? Didn't I multiply the first 2? And then didn't I multiply the outer ones? Did I have to look at it? In fact, looking at it that way takes you away from the idea behind it, when the idea behind it is easy just to use. I don't know if you guys really follow me, but I'm not saying don't use FOIL if you like it. I'm just saying I wish we never taught the damn thing. Because we don't need to.
So the first one's FOIL?
Yeah, this is totally FOIL, but this is kind of like more work than normal just to show you why it works.
Okay.
Right? And then keep going. So this will be negative 2 times 4x. Negative 2 times 3. And then, of course, you put whatever like terms together you got. So you get 20x squared plus 7x minus 6. I like it. Sure. So here's where FOIL lets you down. So if you have a teacher that teaches you FOIL and you totally use FOIL, what are you going to do when you get this problem? What are you going to do? Besides cry, because now you don't, FOIL, now you need something with a M for middle. So it'll be like, fudge. Right? I'm not going to, FOIL's not worth shit here. Yes, but if I, go ahead.
You're just gonna think of it in terms
Yes.
of distributing that 2x.
2x gets a turn,
And then
5 gets a turn. If you look at it that way, it doesn't matter how big either one of them gets. Just whatever's in it, each piece gets a turn to distribute. That is the correct way to look at this. You guys with me? Now, of course, some of you guys have no problem with these. You use FOIL, it works, and you can do these. It's great. That's great. Right. So what do you get here? You get 2x times x squared. 2x cubed. 2x times negative 3x. 2x times 2. And then you get 5 times x squared. I'm going to line up my like terms. Right? 5 times negative 3x. 5 times 2. Poor little 10's got nobody to go with. And then you just put your like terms together. 2x cubed. Negative x squared. Negative 11x. Plus 10. Wow. I like it. By the way, real quick, before I get too far away, I don't want to do another problem. Well, why not? All right, I'm going to do an extra piece that you never have to do for any homework problem. I'm just going to do it right now, just to show you what's going on concretely. What is 2x plus 5? What does it represent?
I don't know.
A number. I love it. So I got a number times another number.
Plus 5.
No, I got a number times another number. I like it. So what could x be? Anything. I love it. So let's pick a value for x. What do you guys want to use?
0.
Yeah.
4.
2. I like it. So x is, let's say x is 2. Stay with me. Stay with me. Now, remember what I just said. That problem's done. What I'm about to do, you never have to do. I just want to show it to you. Just to make this more concrete, what we're doing. What would this number be if x is 2?
9.
Yeah, 4 plus 5. So that would be 9. Times, what would this number be? 4 minus 6 is negative 2. Plus 2. 4 minus 6 is negative 2. Plus 2 is
0.
0. So what should the answer be? What is 9 times 0?
0.
0. So this better come out to be 0 when I put a 2 in for x. So what this is the number that results from this times this when I don't even know what those numbers are. So how many numbers did we just multiply? An infinite number. I might be slightly freaking you guys out, but what could this be? Anything. I can make x anything I want to. It's a polynomial. So there's an infinite number of possible numbers times an infinite number of possible numbers equals an infinite number of possible numbers. If I pick a specific value for x, this number has to equal this number. So if I put a 2 in, I get 2 cubed is 8 times 2 is 16. 2 squared is 4. 2 times 11 is 22. 16 minus 4 is 12. Minus 22 is negative 10. Plus 10 is 0. So if you used x equals 3, if you use x equals 0, if you use x equals 4, you should get a number, number times number, and that comes out to be the same as this. I like it. Now I know on one level that's not very impressive, but that's one reason why this is harder than multiplying numbers, because we're actually multiplying an infinite number of numbers. Holy shit.
Did you know it was going to be 0?
Huh?
Did you know it was going to be 0?
No, I didn't know. Yes?
So that's just like a way you can kind of check yourself. If you're feeling like your answer is incorrect, you just check it like that.
Oh yeah, yeah.
Plug
This
in
is
a number.
one way you can check your work.
Okay.
If you choose a value for x, whatever this times this is, better be what this whole thing comes out to be. Because that's what this says. This is this.
Yeah.
I like it, I like it. Maybe. So here, you guys try this one. And I'll warn you ahead of time, something interesting happens. What you got, Jeff? So multiply that out. So what's the interesting thing that's happening? A lot of stuff cancels, right? So let's see. 2x times 4x squared,
8x cubed,
8x cubed. 2x times 2x,
4x squared,
4x squared. 2x times 1,
2x,
and then you got minus. So basically this is just going to make all these just with negatives. So minus 4x squared, minus 2x, minus 1. So die. And then get ax cubed minus 1. Now that only happens in specific situations. We are going to learn how to start here and work our way back to this. It's not immediately obvious. Right? So future us is going to be all like, I know more than you did past me. Right now you have no idea how this shit, but maybe some of you guys kind of remember. This is called a difference of cubes. Right? 8 is 2 cubed, x cubed is x cubed, 1 is 1 cubed. So if I ever have that, I can factor it as a little piece times a big piece. So we'll see that in chapter 6. What about this guy here? Let's see. Let's do one that's like that, but smaller. So do that one. And then see if you can figure out this one here. What is it, Jeff? I don't know, man. There, it's that one. So what do you guys get here?
16x squared,
What do you think this form's called? No, this is difference of squares. That might sound familiar to some of you guys. If not, it's okay. We'll talk about that later. So how did I make one that worked? What did I do?
Set the inverse of each other.
Yeah, it's gotta be the same stuff with a different sign in the middle. See how that makes the middle terms the same, different sign, so that will always cancel. So a minus b times a plus b, the middle terms cancel. I love it, I love it. What about this guy? The worst thing, if you have this as an answer, just be quiet. Or plus 25%, no. No. What is something squared?
The same thing times 2.
Yeah, so you gotta write it twice so you don't lose terms. I lost my middle term up there. So it's supposed to be 9m minus 5 times 9m minus 5. Then you distribute. I like it, so you get 81m squared minus 45m plus 45m plus 25. 81m squared minus 90m plus 25. Bam. Middle terms don't cancel because they're both the same sign. They're not going to kill each other. Like it.
Nothing called anything.
No. Sorry. Poor little dude.
It's just easy to factor, right?
We'll call it poor little dude. Yeah. When we start factoring, this will be a nice one to factor. Like it. Okay, so. Last idea for the day. Look, it's going to take us a few minutes, but don't get too excited. Without using a calculator, please take a few minutes to figure out what this is. Don't use decimals for the answer. You put it in fraction form, the remainder. So don't put anything 0.000 and go slightly insane. Don't do that to yourself. This is good. You got to remember how this works, because we're about to do it